quantum mechanics, and I think it's our duty to bring leaders in the field of quantum. And here is a particular special case. Professor Chuang, he did his PhD in electrical engineering at MIT, and then he went to Stanford to do a postdoc, and then he came back to MIT, where he has started the ideas of quantum information working with NMR. Then he moved to deal with trap ions. And I think the thing that he's most famous about is for his book in quantum information. I think all of us have read it, has studied it. It's a remarkable book to learn quantum information. And well, we have him today. He's going to do some lab tours tomorrow, and he's going to tell us about quantum computational sensing. So we will all enjoy his talk.
Thank you, Ana Maria. Thank you for the kind introduction, and it's very kind of you also to give me this kind of a warm welcome with standing room only. And there are actually 2 holes. Oh, there's only one now. There's 1 seat left. Two seats here. So if anyone wants a tunnel, or not adiabatically jump into those holes. Anyway, we are at a wonderful moment in our field of quantum information science, and I wanted to start not with the topic of my talk, which is quantum computational sensing, but to pay tribute to some of the pioneers who have recently been recognized in our field, namely John Clark, Michel Devereux, and John Martinez. And they have been recognized by the Nobel Committee for communicating across a divide that we've had in this field, namely between physics and engineering, in the sense that they are one of the first to look at circuits that are quantum mechanical in nature. And why circuits? Because they allow us to see something that's quantum mechanical, like this Rabi oscillation, but they are designed in a way that can, in principle, scale and communicate with large patterns of systems that you can eventually realize. And you may know that John Martinez did much of his early formative work here at NIST. That's when I first met him myself. And then moved, yes, woo, yay, NIST, especially on a day like today. And then he moved to UC Santa Barbara and then to Google. And at Google, he helped pioneer, this is a picture from like 2019. And this is an instance of a much, much larger version of that circuit that you see above there. And today, as you've also heard from the award announcement, Michel Devereux is chief scientist of Google Quantum AI. And it is interesting to understand why companies like Google and so forth are working on this. That's not the story I'm going to tell you, but I'm going to come back to them at the end of my talk. What I want to do, though, is start with the physics story, something that I hope many of you are very familiar with, like the fact that sensing is at the heart of science, and we need better and better sensors for many phenomena. For example, sometimes you want to receive a signal from a spacecraft that is going far out into the interstellar distance, Voyager 1, and then you get very few signals back at the radio telescope here. Maybe you have rare events, such as a gravitational wave collapse from some supernova and multi-messenger things that you need to trigger. Sometimes maybe you have many unknowns, such as in chemistry, where you'd like to find out an answer to a question, even though there are many things you do not know yet. And in these sensing needs, we might ask how we do them today. Well, a traditional sensing paradigm uses a structure like this. Our goal is to estimate some observable, and we do that by repeating a measurement that starts out with some kind of sensor, and we send the result into a computer to process it and then help us analyze those results. And we know that if you average these and they're independent, identically distributed samples, we get an uncertainty and error which drops as the square root of the number of samples. From quantum mechanics, we also know that if we have a quantum sensor, for example, and inject some kind of squeeze state or use entanglement, then in principle, we can get the Heisenberg limit, which scales with the error going as 1 over the number of samples instead of 1 over the square root of the number of samples. So this is very well known, textbook material. And my question to you is, can we do better than this? How can we set up our sensing problem so that we can go beyond these paradigms of the standard quantum limit and the Heisenberg limit? And my answer to you, my claim to you, is that maybe we can do so if we utilize the capabilities of quantum computers. And let me set up the setting in the following way. Our goal of estimating an observable by taking samples is not going to work well for using quantum computers. So let's first change the question that we're going to ask. Instead of estimating an observable, let us ask instead for a decision. For example, if we're looking at few photons, we might ask for the phase of each one of those photons, kind of like we are signaling from Voyager back to Earth. We're using phase shift keying for that. For example, if we are looking for a question about fundamental physics, maybe we don't need to take all the data for a King plot. Maybe we could just ask the system to tell us, was there beyond standard model results or not? Maybe. These are all very speculative, but I want you to conceptualize the role that decisions could make. Maybe we don't need to know exactly whether and what the whoop sound was, but we're maybe quite happy with knowing if something happened or not, so that you could trigger your multi-messenger passageway. Okay? So these are possibilities. And in fact, such kinds of sensing paradigms of making decisions is now part and parcel of much of modern sensing that's not necessarily in physics, but rather in the realm of compressed sensing. So where the sensor, for example, if it's a camera, might only read out the pixels that are needed to tell you if what it sees is a cat, a dog, or a person, or a delivery person. And then it just gives you the category of thing that it's seeing. So if we allow ourselves to change the question that we are asking, then it opens a door for doing something different with our sensing, and that is to put right after the sensor a quantum computer. Take the sensor data, and I'm not talking necessarily just of a quantum sensor. It can be a classical sensor, but have it interact, say, with just one qubit of a quantum computer that it's attached to. The quantum computer, allow it to have lots of memory so that it stays coherent for an arbitrarily long amount of time, just for the sake of argument. And then we process that. And I claim in this talk today that if we do this, a quantum computer can dramatically improve decisions made with quantum and classical sensors that are attached to it beyond what is possible classically. And what I want to do in today's talk is to illustrate this for 3 different scenarios. One which is few photons, where you might ask what is the phase of the photons. One which is about rare events, where you want to figure out which event occurred, given that some event occurred. And the third is that if you have a signal coming and you have many unknowns about the signal, all you care about is to know whether the signal was present or absent. Just as toy models to convince you that there is a plausible scenario that answers those questions. And I'll come back to whether this is and how you get there to do this in make these real at the very end of my talk. So I'll share with you 3 different examples. The first is phase shift keying. The second is quantum trajectory sensing. And third is quantum signal detection, about exactly those 3 thoughts that I just shared. So let's begin with quantum phase shift keying. Here, the scenario is that you have this antenna that is broadcasting a photon, a few photons, actually strong photons, but you only get a few samples of them. And you want to discriminate between whether the photon is causing a rotation of your atom, let's say it's hitting a single trapped ion, whether that phase of the photon is 0, 120, or 240 degrees relative to a carrier. This is a traditional exercise in a lot of engineering called phase shift keying, or signaling by phases. And our goal is to do this with the fewest number of photon batches that you receive. In our quantum mechanics world, we can think of these as rotations around different axes of the block sphere. And because we know these rotations are around different axes that are not orthogonal to each other, we know that they result in a non-orthogonality that requires us to do multiple rounds of that measurement. When we started this experiment, we also realized that this is a traditional and a very well-studied problem in normal signal processing. And there it is called the Mercedes-Benz frame. It's a funny thing because like all these signal processing people know what a Mercedes-Benz is, but not physicists. So we had a lot of fun studying this problem. Classically, with a single shot measurement, you get a success probability of 2/3 because of the non-orthogonality. And quantum mechanically, if you do this sequence over here of here's the query, this is the unknown phase, you set up your system, you do some unitary, you receive another photon, you do another unitary. This is one intermediate readout, and then you repeat the same idea. This will give you the answer in an ideal case with unit probability, so no error, as opposed to this 2/3 when you measure it once immediately like this. So I want to show you how this is done, and I'll come back to why it works in just a moment. So an experiment was carried out by Kyle DeBry in this paper that was published in 2023, where we took a single trapped ion in John Shiverini's lab at MIT Lincoln Laboratory and did the following. So our goal is to realize this sequence of operations. And since we need to measure and distinguish between 3 possibilities, we can't do it with a qubit, a 2-level system. We had to use a larger dimensional Hilbert space just to do the encoding. And it turns out to be very convenient to use the Hilbert space of the d5/2 level of a single ion of calcium 40. So we used 8 states here, the d5/2 and the 2 s1/2 states. And the laser is this 729. And these unitaries are radio frequency pulses that are applied between these metastable states over here. And this experiment looks simple in terms of this diagram. Time goes from left to right in this circuit, but it requires about 28 pulses because of the limitations of what RF you can perform. And that means that we needed a gate fidelity that was high in order to get even just a 10% final fidelity on the error. And then because these are Zeeman levels, we needed an extremely stable magnetic field in order to also get that kind of fidelity. So Kyle came up with a whole scheme. I'm not going to show you much about the experiment, but I'd like you to appreciate a few elements of it. It's a cryogenic experiment. This calcium is held above a microfabricated trap. It's operated about 5 Kelvin. And superconducting niobium rings above and below the trap are used as a miniature Helmholtz coil to stabilize the field. And then we have the usual rest of a trapped ion experiment. Is that fair, Didi? There are a few more details. And then in this experiment, Kyle was able to do the following. He ran the sequence of unitaries, and for debugging purposes, he took measurements of the final probabilities of all the levels. And this is what we get for the 3 cases of 0, 120, and 240 degrees of RF coming in. And this is time going from left to right. And this is the probability of the different measurement levels, where we show just 3 levels corresponding to what is measured to determine whether you have 0, 120, or 240. So you can see that in the first sequence, the green is high at the end. In the second one, blue is high. And the third, the pink is high. And it was high with a fidelity of better than 99% at the end. Kyle really worked very, very hard to remove almost all sources of systematic and random noise from this experiment. And this meant that not only did we have such a good result, and we got this for phase shift keying, but also amplitude shift keying, it implied that per pulse, we had an operation fidelity that was almost at 4 nines of fidelity. This was the most complex and highest fidelity operation that we have performed in quantum computation at MIT. So that's not the story for today. What I want to share with you is that this is a kind of expected result because almost everything is predictable with trapped ions. What I want to share with you is that you can actually do this and understand a key piece of intuition that's really neat about what you might generalize it for the task of sensing. So the key idea is to interleave the signal with a processing pulse. The processing pulses are these unitaries. These are the signals that are coming in. And what happens when you take just to think of this as a 2-level system at first, is that the probability of measuring a 1 over here is a polynomial in the phase of these 2 things. And we can write out that polynomial just by plotting it. And since there are two queries to it here, the polynomial is going to look like this. It has two zeros. It's like an order 2 polynomial. And here we have 0, 120, and 240. And this means that the final result at the end over here will be 1 if the phase was 0, and 0 if it were these two phases. I didn't tell you how we got the polynomial, but we know that the probability of these operations has to be a polynomial when you just multiply the matrices together. So if I had some way of coming up with this polynomial, I'd have a really neat filter that filters out and looks for this one. And we can do the same thing by cascading another stage here that filters and finds the other case. So now we have something that filters out this 120-degree result and then rejects the 0 and 240. And if we put a pulse in the middle that does an intermediate readout, then we would get these three results, 1, 0, 0, 1, and 0, 0, as the readouts for the three possible phases corresponding to phi. So this is an instance of a technique called quantum signal processing, and a shout out to the group at Quantinuum who had a really neat realization of this in trapped ions at around the same time we were doing this work. But for the sake of today's talk, what I would like you to go away realizing is that there's a recipe. There's an amazing theorem that says that you can choose the polynomial you would like to realize, and there is an algorithm to find the sequence of phases for these unitaries U that will converge, is easy to run, is fast, and it will give you the filter that you desire. This is special. It's an inverse problem that's solvable, and it's very rare. And this is called the quantum signal processing theorem. And that is a useful tool because many of you who are doing experiments would like to filter out one thing or another. And in digital signal filtering, that's a basic idea. So for this first one, take away the idea that you can design tailored filters using this technique called quantum signal processing, and then utilize that for sensing tasks such as measuring the phase of a photon with very few queries. OK. Yes, question?
Yeah, can you comment on sort of satisfying uncertainty principle? Usually that's what the Heisenberg limit is. So what is the...
Absolutely. So the question is, can I comment on the Heisenberg uncertainty principle for this? In fact, there's a beautiful Heisenberg-like uncertainty principle for exactly this, which is that the sharpness of the polynomial, which will be the error, goes as 1 over the degree of the polynomial. So the sharper you want your decision to be, the longer the sequence of the polynomial you have to run. And the degree of the polynomial is exactly the number of queries you make to this unknown signal. And it's a linear relationship. So you can say error times complexity, which is the 1 over the degree, is a constant. And that's kind of like a Heisenberg uncertainty principle for this quantum signal processing. And it's not a surprise because there's a kind of Fourier-like relationship between those two.
But then why are you doing so well with only second-degree polynomial?
Because we did 2 polynomials there, and thus could filter out the 3 signals. And then you can show that that generalizes to an arbitrary number of phases if you want to do a constellation of phases in decoding. Thank you for the question. Others? OK, so let me share with you the second thought, which is quantum trajectory sensing. So now what I'd like to look at is which event happened, because maybe we have rare events. And in this scenario, imagine that you were given an array of sensors. Think of these as qubits. And then something runs across the qubits, and it rotates each one of them by some angle theta. Your goal is to figure out whether the path went that way, or this way, or whichever trajectory. And you want to distinguish all of them as well as possible. And this theta we'll call the interaction strength, and it'll be between 0 and pi. If it's a pi rotation that's just like a perfect flip, and it's like a perfect classical scenario, and this trajectory will only happen once. That's the notion of rare event. We want to be able to distinguish them, distinguish which trajectory happened with as much certainty as possible. Classically, that means we have these independent sensor bits around. It's very clear that you must have theta equal pi for 0 error, flip or no flip, because otherwise you'll have something statistical, like this is 0 or 1, 0 or 1, or 0 or 1 beneath that trajectory. Quantum mechanically, it turns out that you do not need a pi interaction strength. It suffices to have this theta be between 3 pi over 4 and pi for a scenario I'll show you in just a moment. And if that's true, then you can actually distinguish all of the trajectories for the scenario with 0 error. And the reason that's possible is because we can start this sensor array in an entangled state. We then measure it in some collective way, so that may be a difficult measurement, but it's really neat that it's possible at all to distinguish something. And the reason that works is we start with an entangled state, we prepare that, we then interact, and this is not an entangling operation, it's just a crossover that does a tensor product operation, and then measure in some collective way. So here's a scenario I'll show you specifically. Imagine that you have 4 of these qubits. The trajectory goes around and it shifts the phase of the qubits by angle theta. Then we can show that if you plot the failure probability of the distinguishing the trajectories as a function of theta in units of pi, classically it's the blue line here, and quantum mechanically the error is this red line here. And you see this range of thetas for which the quantum has 0 error and the classical has some non-zero error. But uniformly in this range, the quantum mechanical system works better than the classical can. Of course, this is in a perfect scenario with perfect entanglement, noiseless measurement, and so forth. So it's not necessarily going to reflect what you do in a realistic system, but it gives you promise. Why does this work? Well, the interesting thing is this 0 error case is really unexpected in many ways. For example, consider 2 qubits and theta being pi over 2, so a 90-degree pulse. A classical protocol would start out with qubits that are unentangled. Let's say they're in the plus state. And then the beam goes by and shifts each one of these by a factor of I. So that means we would get 0 plus I1 twice. And when you measure this, you'd get some random result if you measured it in the computational basis. In contrast, as an exercise in quantum mechanics, you've probably seen many times that if you had started this in a singlet state and then had the factor of I come through, the I would add to this one, the I would add to this one, and that would factor out as an overall combination of 2 factors of I, so you would get this other entangled state instead. And you can uniquely, you've added up the phases because that singlet state acts something like a long baseline that combines phases across multiple qubits. So that's conceptually why you might be able to expect that trajectories across entangled states would be able to add up multiple phases. But of course, there's a contradiction here because this uses entanglement, and entanglement is known as being monogamous. In other words, if 2 systems are maximally entangled, they cannot be entangled with a 3rd system. So I might be able to use that singlet state to add up the phase between 1 and 2, but then what about 1 and 4 and 1 and 3 and so forth? It wasn't expected that this kind of entangled state would allow you to add up lots of phases and then distinguish all of these trajectories. But our scenario is slightly different, and in fact, we do not yet understand in the world of theory today very well multipartite entanglement. So we use multipartite entanglement, and we also use non-maximally entangled states. Many of you have worked with W states and other kinds of states like that and found that they are very useful. Here, we found something really fascinating, which is that it's actually useful to use quantum error correction code states. And these are states that are also not maximally entangled, and they are multipartite entanglement. I'll show you a table of mapping between the 2 concepts of error correction and trajectory sensing. And the idea is that normally in error correction, an error is to be corrected and then gotten rid of. But our scenario says the error is what we want to learn about. It's the trajectory to be sensed. Thus, the syndrome that tells you which error happened tells us which trajectory happened. In fact, if we want long trajectory paths, they are like statistically correlated errors. And also, the sensor state criteria for trajectories turns out to also be the error correction criteria, the nil-Laflamme conditions. And in trajectory sensing, we don't need to encode a qubit, but most quantum error correction codes do that. Although there are like 603 codes that encode no qubit in the NKD parameter regime. So what we have discovered in this research is that non-degenerate stabilizer codes designed for correlated errors, such as cosmic ray muons hitting a superconducting processor, it wants to correct the correlated errors from that, and the error syndrome can tell you which path the cosmic ray muon took. And that makes it a good sensor state. Also, we found that there are non-stabilizer codes that have never been known before, or even no use for them known. And now we know a very neat use for them, which is for trajectory sensing. So the third idea I want to share with you is that maybe a neat takeaway is that we could use in this community the states of quantum error correction codes as sensor states. These are sensor states that can be tuned to sense exactly what you want by designing the codes to be sensitive to the thing you're trying to sense. And maybe this is a useful strategy. So that's my second story here. Questions? Yes, please.
Sorry, you just were saying it kind of, in the previous example of the cosmic ray muon, it seems like the qubits are the sensors, but I feel like in the beginning, because you said that you have like a quantum sensor and then a quantum computer immediately following it, like doing the processing. Is there a distinction, or is it like in that particular case, or are they the same thing?
Here, the quantum computer has, you might think, every qubit attached being a sensor. But if you wanted to make this realistically, you'd probably have to have some kind of fault tolerance. In other words, those would be logical qubits. And maybe you have one qubit exposed as a sensor, and then it feeds its signal down into a quantum computer that's busy doing error correction to keep it fault tolerant and coherent for a long time. So yes, I wasn't clear about what's the sensor or what's the computer in this scenario, but there are all sorts of ways you can construct it like you're imagining. Good. Yes, please, Chi.
So you briefly mentioned that to do this you need a collective measurement, and why exactly do you need a collective state readout?
Right, so Chistos's question is, why do we need a collective readout? It's because the entangled state is going to be orthogonal to the states of the entangled states are mutually orthogonal depending on which trajectory path happened, but they're very strange entangled states. And so they have to be distinguished from each other. You can use things like a toric code for that. And the toric code would have small wave stabilizers that would be easier to measure that would allow you to do some distinguishing. So it depends on what states you want to distinguish between. And I don't have a general answer on how hard it would be to do those measurements. But of course, that matters a lot to experimentalists. Good question. Yes, please.
Where the signal is coming, from the left side on the right side, or this quantum trajectory?
So the question is, can we distinguish in this case whether the signals, the trajectory is coming in from the left side or the right side? In the examples I've given you, the answer is no. But I think you could come up with other scenarios where that is true. But just not in the ones that I described. Yes, please.
How does the size of the error correcting code, like the number of qubits, scale with the length of the trajectory?
Right. So it depends on the size of the set of trajectories you want to distinguish. And I think probably the best way to think about it is that the number of trajectories you can distinguish is something like 2 to the number of possible syndrome values that you can measure, in an ideal case. But But then you have to be careful about exactly which trajectories are there are, because error correction codes come in all sorts of forms and ways. So go find your favorite quantum error correction theorist. I think one is sitting right next to you, and get him to tell you about how they translate into sensing requirements. And that's the new idea that's coming out, because many error correction theorists have never thought of their codes as something useful for sensing. OK, let me move on for now and try to share with you the last example, which is about quantum signal detection. And in this case, we want to ask if just the signal exists or not. And here's the setup. Suppose we have a magnetic field. The magnetic field has a strength that is unknown, a frequency that's unknown, and a phase that's unknown, although we do have some bounds on them. So this could be a scenario that's realistic, coming from the outer space or from some molecule. And we can formally define this problem as something I'll call AC B min delta omega, where we are told that the signal is at least stronger than some B min and exists in some bandwidth delta omega. And we want to answer whether or not this signal exists in some minimum time. And we do not care about finding out B or the frequency or the phase. And this kind of a decision problem might be a practical one, because you often do want to just know if something exists or not before you then go to the trouble of learning more about the signal. And how well is this done? How do we set up this problem? Well, let's imagine that it's an interaction Hamiltonian between this magnetic field and a number of spins, which we'll call n sub s. These will be the sensor spins. But they're just two-level systems. And then we'll connect these two-level systems to our quantum computer. So I'll be explicit about that here. But the signal only affects these sensor qubits. It turns out then the best strategy for sensing is to search the number of frequency bins, which is delta omega divided by this small delta omega, which I'll define in just a moment. And it is because of this necessity to search. You search here and use the best possible method that you can do for a given bound on B min. And ask, how long does this take? So let's work that out. If we are searching over these kinds of bins, it turns out that the optimal bins to take in a reasonable set of parameter space, that is, B min is not too small, and delta omega is reasonably large, then in kind of reasonably intuitive units, the amount of time that you want to spend is going to go as 1 over the minimum strength field. And similarly for the bandwidth over here of each search unit space. And then the total time is going to be the number of bins that we search times t. So if we calculate that the number of bins is the total bandwidth divided by this range, then the total number of bins goes something like this expression here, which is the total bandwidth divided by the square of the minimum signal strength. This is with one sensor. And already with just this one sensor, we can look at an interesting range of possibilities in this phase space of sensitivity and bandwidth. So I've colored in a regime here where this is the regime of detectable signals given a fixed sensing time tau. If we increase the number of sensors, then that changes the sensitivity. And let's say we do this in the best possible way, so that it's a Heisenberg limited sensitivity. Then we see that the best possible is now delta omega divided by n squared b squared. And that gives us a Heisenberg limit over here. However, there's a search problem together with this signal kind of identification problem. And given that there's a search problem, you might say, well, there's actually something I can do with a quantum computer if only I could utilize this in the framework of quantum algorithms. And that is, maybe I could use this quantum computer to do a search. And if I do a search with a quantum computer, then it turns out that you can prove that there exists a quantum computing sensing algorithm to solve this in a time which has the square root of the number of bins to search because you run Grover's algorithm. It requires you to do something weird, which is searching in superposition. But it's plausible and possible as long as you have a quantum computer that is sufficiently coherent over the time that you're doing the searching. And so we proved this theorem as well as a second theorem. This algorithm we call quantum search sensing, and I'll come back to its intuition in a moment. And the second theorem we prove is that that's the best possible. And therefore, we call this the Grover-Heisenberg limit. It's a nearly identical expression up to some small factors. And that means that this algorithm is an optimal algorithm up to these polylogarithmic factors. And we can plot the range of what's possible with this in this diagram, showing that you can exceed the Heisenberg limit in solving this decision problem. It's not an estimation problem, because the estimation problem would have as its best possible the Heisenberg limit. But because we're a decision problem, we can do better than that. And this thing we call the Grover-Heisenberg limit. And I want to share with you why this is possible, what makes quantum search sensing possible. And the key idea behind this is that we started with an analog evolution given by this interaction Hamiltonian, which has these analog continuous phase shifts as a function of B and the phase phi, which is very awkward for a quantum algorithm. Quantum algorithms like Grover's search are not designed to utilize these kinds of analog phase shifts. So what Soon-Won Choi realized, conceptualized, was a very clever idea, which is, let us digitize that oracle, come up with a series of procedures that allows us to transform this analog evolution into a step function. And once it's in this step function, we can run Grover's algorithm. And this digitization of a oracle that's getting the signal is done in this work by first utilizing an AC Stark shift and adiabatic ramping to make it insensitive to the phase phi. Second, by sensing in superposition by creating something that is called in the paper an elementary sensing unit that allows us to have a phase shift, Z phase shift of each of the sensor qubits that is insensitive, that is independent of phi. And then third, using quantum signal processing to make this a step function instead of a smooth function. And so these three ideas are pretty generic and can widely be used. And that is my third takeaway idea to you, that there is now a concept of digitizing quantum sensors such that they can be utilized in quantum algorithms. And although we have shown it just for Grover's algorithm, you can imagine sensing problems where, for example, the signal might be encoded in the product of two integers. And if that were the case, then maybe the algorithm you would need to be able to figure out whether the signal existed or not would be a factoring algorithm. And then maybe you would have an exponential advantage here for that kind of an encoded signal. And other cases too, where algorithms can come and help you. So I hope that you've appreciated that there's a little bit of thread to pull on here for quantum computers and quantum sensing. Let me end by sharing with you a broader perspective with a shout out to a nice paper which I've really appreciated from Peter McMahon's group at Cornell. This is a review paper, Quantum Computational Sensing Advantage, in which he goes through a wide range of techniques that go beyond the toolbox that I have just shown you. And this is shown in this beautiful figure, large figure that he has of lots and lots of modern techniques now that have been developed over the last decade. He breaks it up into old stuff here. I know some of you have worked on these here. And then the things he's calling quantum computational sensing, which involves, for example, the trajectory sensing I showed you, a bosonic sensing technique, which I wasn't able to share with you, signal processing, and this enhanced Grover sensing that I did share with you. So it goes way beyond just the three I shared. And this is an exciting area for the community. And I hope that you have appreciated how you can now think of designing tailored filters using quantum signal processing. You can now think of using quantum error correction codes as sensor states. You can now think of using digitization of quantum sensors so that quantum algorithms can apply. And what does the future hold? Where should we go with this? I believe that the biggest challenge in this direction is actually reducing it to practice. We need to find a way to couple quantum sensors to quantum computers, ideally large quantum computers. And that means that it's no longer going to be in the domain of just physics. It's going to need serious engineering. It's going to need a collaboration. It's almost like a grand challenge for the unified domain of physics and engineering together, so that maybe it enables a whole new range of physics after that. And so you can imagine maybe in some future world, what you have is a large quantum computer, such as a Google Sycamore chip, and then connected to that some kind of quantum USB bus and some cable that goes between Didi's lab and a sensor. Well, let's stick the quantum computer somewhere other than Didi's lab. And then maybe together this will work. But it needs a quantum computer agnostic universal connection so that we can develop quantum peripherals that can connect sensors to these machines. And maybe then finally, those big commercial quantum computers will find some use. Thank you.
Thank you all for the very nice talk. So we are open for questions. Maybe I can start. Oh, there is already
Didi.
one. Okay, Didi.
Thank you, Ike. I was wondering, you're saying quantum error correction codes are necessary or are related to your detection problem. So do you really need correction, or is error detection code enough? And also, what happens to the qubit in the error correction code? Can you also use that?
So the question is, what happens, do we need correction, or is a detection code sufficient? What happens to the qubit in that code? So the only thing we need is that the syndromes uniquely identify the trajectories or whatever you're trying to sense. And if a detection code provides that level, then it's perfectly fine. Typically, as the distance of the code gets larger, the number of errors that you can distinguish uniquely grows. So that's a mixed answer to your question. The second part is, do we need the encoded qubit, or what could we make of use of the encoded qubit? Actually, the encoded qubit might be useful in making the sensor state itself fault tolerant. What you do is you use that qubit to test if there was an error in the sensing system. So the role of the qubit now flips with the role of the error. The qubit that you had encoded is something we'll throw away and use as a sensor and a diagnostic.
Maybe I can ask a question. So at the beginning you have a scheme where you were saying sensor, and then you were putting a quantum computer next to it. But it's not better to have before the sensor to create a state that is typically you first create the entanglement, you sense, and you do the entanglement. So is there anything that you can add before, or is the sequence that you gave really the one that we want, or there are possibilities that we can do before?
Thank you, Ana Maria. So the question is, I have a quantum computer after the sensor, but clearly sometimes you want to create some kind of neat sensor state, do the sensing, and then maybe analyze it with the quantum computer. And I have shifted what I mean by the diagram in the presentation. In those first few slides, I'm just talking about connectivity, really. So oftentimes the quantum computer will do something first with the sensor, exactly like you're saying. And then I shifted to making it time, but I didn't explain that properly.
Okay. More questions?
Thank you for the amazing talk. As with the quantum computing, it's really hard to compete with classical computers that are amazing. And similarly, it's really hard to compete with classical sensors that are also really good and usually improve them by putting more atoms or something. Can you envision some sweet area where this approach would give some quantum advantage in sensing, where it's more practical to do the quantum computing assisted sensing to beat the classical sensors?
Everything was great until you said the word practical. So I've shown you lots of theoretical ideas, and I'm hoping that you in the audience here will find something practical to make out of it, honestly. However, the paper by Soonwon Choi, Richard Allen, and company, Robert Wang was another co-author of that, has a very nice, thorough analysis by Francesco Machado, one of the co-authors, about an NV center scenario with more or less realistic numbers about dephasing in the NV center. And it does seem like there is a regime for magnetic field sensing, detecting the existence or absence of a magnetic field of unknown amplitude, phase, and frequency, where an NV center might be able to do that realistically. And there you can imagine an NV center system with a biological molecule on top, and then you do the readout. Now, how large a quantum computer do you need for that? In their analysis, it's an analysis of principle, and that the quantum computer is assumed to be kind of perfect for that, or post-process just to show a first principles experiment. Because a lot of whether it'll work or not depends on the quantum interconnect. That thing I draw here in cartoon form as a quantum USB bus doesn't exist today, although there are lots of indications that you could make that. For example, Andreas Wallraff has a beautiful experiment showing the connection of two dilution refrigerators with a big coaxial waveguide at 15 millikelvin or something. And he can show EPR pair violation with a long separation, many, many meters between the two dual fridges. So we know how to do some kinds of interconnects. And there's lots of work that's happening here, for example, on optical interconnects and transduction. So the hope is that that might work out, but a lot of the practicality depends on that interconnect.
For the last part of the talk, is there an intuition for why Grover search is actually optimal? I might have thought that there were other algorithms, like something Fourier transform direction that might do that.
Right, so the question was in the last part of my talk, is it clear that the Grover algorithm is the optimal algorithm? It does saturate our bounds on what is possible, and we compute those bounds without reference to any algorithm, and instead using the Fisher information and optimizing it. So since it saturates that bound, we're pretty satisfied with that. But another argument is that if you want to find a needle in the haystack and don't have extra prior information, then the Grover algorithm is the best that you can do. And there's a polynomial bound that you can prove on that kind of search scenario. Of course, in a realistic situation, it might not be that it's just searching across all the bins. If you have extra prior information about the structure of where the signal is hidden, then you would probably apply a different algorithm that specialized that prior information. And that could be a maximum likelihood kind of algorithm instead. And so by all means, the algorithm will change as the kind of nature of the hiding of the signal changes.
On this last point, do you think you could kind of go backwards and say to use like some sense of protocol to motivate new quantum algorithms, like digitization or analog digitization?
Great. So could we utilize sensing problems to motivate new algorithms? And the answer is absolutely yes. In fact, in some of the scenarios which are shown in Peter McMahon's group's review paper, they do not have explicit algorithms, but the scenario uses a trained quantum system. So if you want to use the words quantum machine learning, it trains a unitary with the appropriate parameters to be able to do the distinguishing. And really, it's a class of algorithms that's being utilized, and then in that case, found. And I bet that you might be able to motivate lots of interesting algorithms using that direction, because that's certainly been true about compressed sensing. Just look at the analog in the purely classical world. There are a whole varieties of new classical transforms that have come out, such as wavelet transforms, and many more. The faster than fast Fourier transform, which works faster than n log n. for finding these kinds of signals when you have prior information about the structure that you're looking for.
I have a conceptual question. So I think what makes a quantum computer good naively is that it's insensitive to the environment noise. On the other hand, what makes a sensor good is that it's sensitive to these things. Right? So now you entangle them. So conceptually, how do you understand that now you have the best of both worlds together while they're entangled?
Great, thank you for the question, which was conceptually, we want to keep a quantum computer away from noise, and we want to keep a sensor as close to a signal as possible. And how do we resolve this kinds of tension? Well, the same might be said of a classical computer and a classical sensor. And here we will say that the quantum computer will be isolated from the signal because the sensor will be in middle. And that will be the role of this cable that goes between the two systems. The cable will act as maybe a one-way filter or a limited bandwidth thing that only communicates just what is needed from the sensor to the quantum computer. Of course, like Google and IBM do not want you to open up their machine. So this cable will be the thing that protects that part and isolates them in an abstraction. I hope that answers the question.
Yeah, I was wondering for the last part, how does the, your signal detection, just deciding, depends on this minimum magnetic field that you're deciding between?
Yeah, how does the signal detection depend on the minimum magnetic field? So, yeah, so right here, I give the bound, and it goes as 1 over this beam in to the 3/2 power, as opposed to the best classical, which is 1 over b min squared. So this is the Grover search bound, and the classical best bound would be this one, which is 1 over b min squared. So it's not an exponential improvement. It's a purely polynomial improvement just due to the square root factor from Grover's search algorithm.